Hello, my name is Abdullah Giray Yağlıkçı, and I will be presenting our work BlockHammer, Preventing RowHammer at Low Cost by Blacklisting Rapidly Accessed DRAM Rows. I will first begin with an executive summary. RowHammer is a worsening DRAM reliability and security problem. However, state-of-the-art RowHammer mitigation mechanisms face limitations supporting current and future commodity DRAM chips because of two reasons: limited scalability with worsening RowHammer vulnerability, and limited compatibility with commodity DRAM chips. The goal of this work is to efficiently and scalably prevent RowHammer bit flips without knowledge of or modifications to DRAM internals. Our key idea to achieve this goal is to selectively throttle memory accesses that may cause RowHammer bit flips. Our mechanism, BlockHammer, performs three operations. First, it tracks activation rates of all rows using area-efficient Bloom filters. Second, it throttles row activations that could lead to RowHammer bit flips. And third, it identifies and throttles the threads that perform RowHammer attacks. We evaluate BlockHammer's scalability with worsening RowHammer and demonstrate that BlockHammer is competitive with state-of-the-art RowHammer mitigation mechanisms when there is no attack in the system. And it provides significantly higher performance and lower DRAM energy consumption when a RowHammer attack is present. BlockHammer is compatible with commodity DRAM chips because it does neither require proprietary information of DRAM internals nor modifications to DRAM circuitry. This is the outline of the talk today. Let's begin with a brief DRAM background. A processor's memory controller communicates with a set of DRAM chips called a DRAM rank through a memory channel. Each DRAM chip contains multiple banks. DRAM cells are organized as an array within each bank. Here's a simplified diagram of a DRAM cell where the data is stored as capacitor voltage and accessed through the access transistor. To access a DRAM cell, its row is activated by fetching the data stored in the cell capacitor into the row buffer. Here we have a simplified diagram of the capacitor voltage over time. We see that the voltage decreases over time in an exponential decay. There is a threshold voltage Vmin, above which the stored data can be read successfully. However, as soon as the voltage drops below Vmin, a bit flip can occur. In order to prevent failures from charge leakage, periodic refresh operations are issued to restore the capacitor voltage. The interval between refresh commands are referred to as the refresh window. Let's look at the RowHammer phenomenon next. In order to access data from a DRAM row, say row 2 in this case, the memory controller must first open or activate the row. After all requests are serviced from row 2, the memory controller must close or precharge the row in order to begin accessing data from another row. Due to an increase in cell-to-cell interference, rapidly activating and precharging a DRAM row can result in bit flips in physically adjacent rows. Continuing to access the same row results in even more failures in nearby rows. This phenomenon is known as RowHammer. We refer to the rapidly accessed row as an aggressor row, and the rows containing bit flips as victim rows. Let's continue with the motivation. There are four high-level RowHammer mitigation approaches. The first approach is to increase the refresh rate, which reduces the refresh window, and thus the activation count that an attacker can reach in a refresh window. The second approach is to physically isolate potential victim rows with sensitive data from aggressor rows that a potential attacker can hammer by allocating isolation rows in between, such that the attacker cannot disturb sensitive data by performing RowHammer attack. The third approach is reactive refresh. In this approach, when an aggressor row is hammered, potential victim rows are refreshed to avoid bit flips. And the fourth approach suggests throttling or slowing down memory accesses proactively, such that no row's activation rate can reach RowHammer threshold. Unfortunately, existing mechanisms face two key challenges. Let's begin with the scalability challenge. Recent work show that DRAM chips become more vulnerable to RowHammer in the last decade. RowHammer bit flips can occur in much lower activation counts today, and hammering a row can disturb more rows than before. And furthermore, in-DRAM mitigation mechanisms are also shown to be ineffective. Therefore, RowHammer is a more serious problem than ever today. As DRAM chips become more vulnerable to RowHammer, increased refresh rate requires refreshing all rows more frequently, and it is not sustainable due to large number of rows that need to be refreshed. Physical isolation requires allocating more isolation rows. Reactive refresh needs refreshing more potential victim rows more frequently. And proactive throttling slows down the system furthermore. Therefore, Scalability with worsening RowHammer vulnerability is a significant challenge for all mitigation approaches. The second challenge is compatibility with commodity DRAM chips. To understand this challenge, we need to revisit how memory addresses are mapped to DRAM cells through several abstraction levels. Virtual memory addresses are used in application level. Then typically the system software translates virtual addresses to physical addresses. A physical memory address is mapped to addresses of DRAM channel, rank, bank, row, and column within the memory controller. So far, all these address translations are visible within the processor. However, additional to these, logical row and column addresses are mapped to physical rows and columns within the DRAM chip, which is not visible to the rest of the system. DRAM vendors apply this in-DRAM mapping for two reasons: to enable circuit design optimizations to meet density, performance, and power constraints, and for improving their yield by mapping faulty rows and columns to redundant ones. Therefore, in-DRAM mapping includes insights into chip design and manufacturing quality, and that is why it is proprietary information. Unfortunately, physical isolation and reactive refresh needs this proprietary information to identify which rows to isolate or refresh. To address these two challenges, our goal in this paper is to prevent RowHammer efficiently and scalably without knowledge of or modifications to DRAM internals. Let's look into our mechanism, BlockHammer. BlockHammer's key idea is to selectively throttle memory accesses that may cause RowHammer bit flips. BlockHammer consists of two mechanisms, row blocker and attack throttler. Row blocker tracks row activation rates using area-efficient balloon filters, blacklists rows that are activated at a high rate, and it throttles or enforces a certain delay between activations targeting a blacklisted row. By doing so, row blocker ensures that no row can be activated at a high enough rate to induce RowHammer bit flips. An attack throttler identifies threads that try activating blacklisted rows and reduces their memory bandwidth consumption by throttling their memory requests. And by doing so, attack throttler greatly reduces the performance degradation and energy wastage a RowHammer attack inflicts on a system. I will explain how row blocker works next. Row blocker modifies the memory request scheduler to throttle row activations that could lead to bit flips. To do so, it blacklists rows with high activation rates and delays subsequent activations targeting them. We call the blacklisting logic row blocker BL and the delaying logic row blocker HB. To throttle row activations with a high activation rate, row blocker blocks a row activation if the row is both blacklisted and recently activated. This slide explains how row blocker operates in high level. First, memory request scheduler pings row blocker with a "Is the row activation RowHammer safe?" query, before performing the row activation, of course. And row blocker simultaneously checks both components. If a row is blacklisted and recently activated, activating this row can be unsafe at this moment. Therefore, the row activation is blocked, and meanwhile, other requests in the request queue can be serviced. When the memory request scheduler issues a row activation, both components are updated with the row activation information. Row blocker BL or blacklisting logic tracks row activation rates and blacklists a row when its activation count in a time window exceeds the threshold. To do this in an area-efficient way, it employs two counting balloon filters. A counting balloon filter is essentially an array of counters addressed by hashed identifiers. When a row A is activated, its row ID is provided to a set of hash functions that evaluate a set of indices to the counter array, each of which is incremented as shown in the figure. Activating another row, say row B, increments another subset of counters. As shown here, a counter can be used for more than one row IDs. Therefore, a row's activation count can be observed more than its actual value, leading to false positives. We estimate a row's activation count as the minimum value across all of its corresponding counters. These counters are never decremented, therefore a row's activation count cannot be observed less than its actual value, hence there are no false negatives. And the counters can saturate as they are never decremented. To avoid this, we periodically reset them without losing data by adopting a time interleaving approach. I will explain this time interleaving approach next. Blacklisting logic employs two counting balloon filters. A new row activation is inserted in both filters at all times. Only one filter responds to test queries at a given time that we call the active filter. The active filter alternates at every epoch between two filters. Now let's look at the operation of two filters CBF-A and CBF-B across the timeline shown here. A green bar indicates in this timeline that the filter is active at a given time, and we call the other filter passive and indicate its state with a gray bar. For example, at timestamp 1, CBF-A is active. Now assume that a row is activated at a high rate in epochs 1 and 2, and at a low rate later on. RowBlocker blacklists a row if the row's activation count reaches the blacklisting threshold called NBL. Now a blue bar shows that the row's activation count is below the blacklisting threshold, and therefore it is not blacklisted yet. However, at timestamp 2, the row's activation count reached blacklisting threshold NBL, and the row is blacklisted as we indicate by the red bar. At timestamp 3, the active filter CBF-A is cleared, and CBF-B becomes the active filter for epoch 2. Since CBF-B remembers the high activation rate from epoch 1, it keeps the row blacklisted until end of epoch 2. And meanwhile, at timestamp 4, row's activation counters in CBF-A exceeds the blacklisting threshold again. At the end of epoch 2 at timestamp 5, CBF-B is cleared, and CBF-A becomes the active filter again, and it immediately blacklists the row because its counters reached NBL at timestamp 4. Assuming that the row is no longer rapidly activated during epoch 3, its counters in CBF-B remains below the blacklisting threshold, and it is no longer blacklisted starting from timestamp 6. Now, to ensure RowHammer safe operation, RowBlocker limits the activation rate of blacklisted rows at a RowHammer safe level. Now we need to define what is RowHammer safe level. An activation rate is RowHammer safe if it is smaller than the ratio of RowHammer threshold to the refresh window. RowBlocker ensures this activation rate within the lifetime of each quantum balloon filter TCBF, which is bounded by clear operations. Therefore, we write the RowHammer safe condition as activation rate in a TCBF to be smaller than or equal to NRH row activations per TRFW refresh window. And we denote the number of activations in a TCBF as NCBF, and we derive the shown constraints for RowHammer safety. RowBlocker HB is the component which ensures that all rows experience a RowHammer safe activation rate. I will explain how this mechanism works on a timeline. Within a TCBF time window, RowBlocker limits a row's activation count to NCBF. Now, assume that an attacker tries hammering a row as rapidly as possible. Each spike in this illustration represents a row activation. Due to the spikes, there has to be a minimum time window between subsequent activations called TRC. Therefore, a row's activation count can reach the blacklisting threshold NBL at the minimum time window of TRC times NBL. At this point, the row is blacklisted, and subsequent activations targeting the row are throttled until the end of TCBF time window. A red spike represents an activation targeting the row when the row is blacklisted. And to throttle subsequent row activations, RowBlocker ensures a minimum time delay between them, called T-delay. Therefore, a row can be activated at most this many times when it is blacklisted. And by configuring T-delay in this expression, RowBlocker limits NCBF. Please refer to the full paper for more details about this calculation. RowBlocker HB ensures that no subsequent blacklisted row activations is performed sooner than T-delay. To do so, it implements a history buffer that contains the information of all row activations that can fit in a T-delay time window. A blacklisted row activation is blocked as long as a valid activation record of the row exists in the history buffer. In other words, the row is recently activated. This way, no row can be activated at a high enough rate to induce bit flips. RowBlocker already guarantees a RowHammer safe operation. Now I will explain how Attack Throttler improves performance and energy consumption. Attack Throttler tackles the performance degradation and energy wastage that a RowHammer attack causes. To identify and reduce the negative impact of a RowHammer attack, Attack Throttler leverages the observation that a RowHammer attack intrinsically keeps activating blacklisted rows. To this end, Attack Throttler introduces a new metric called RowHammer Likelihood Index, or in short, RHLI. We calculate RHLI as the number of blacklisted row activations normalized to the maximum number of blacklisted row activations that BlockHammer allows. RHLI becomes 0 for benign threads that do not try activating any blacklisted rows, and RHLI becomes 1 when the thread's row activation count reaches RowHammer threshold, meaning that the thread performs RowHammer attack. RHLI of a thread increases when the thread behaves more similar to a RowHammer attack. Attack throttler applies a smaller quota of a thread's in-flight request count as RHLI increases. If RHLI is 0, no quota is applied as the thread is benign. And when RHLI reaches 1, no request is allowed as the thread performs a RowHammer attack. Through this throttling, attack throttler reduces a thread's memory bandwidth consumption proportional to its similarity to a RowHammer attack, and therefore it frees up memory bandwidth for concurrent benign applications. By doing so, attack throttler greatly reduces the performance degradation and energy wastage a RowHammer attack inflicts on the system. Alternatively, RHLI can also be used as a RowHammer attack indicator by the system software for software-level countermeasures. I will share the key evaluation results next. We analyze and compare BlockHammer's hardware complexity with 6 state-of-the-art RowHammer mitigation mechanisms, namely PARA, ProHit, MRLog, CBT, Twice, and Graphene. We calculate hardware complexity in terms of area, access energy, and static power consumption for a RowHammer threshold of 32K, which is a realistic assumption for current DRAM chips. We observe that BlockHammer is low-cost and competitive with state-of-the-art RowHammer mitigation mechanisms. To understand how hardware complexity scales with worsening RowHammer vulnerability, we repeat the analysis for a RowHammer threshold of 1K, which is projected for future DRAM chips. We compare how the complexity of each mechanism changes in terms of chip area, access energy, and static power consumption. We observe that BlockHammer's hardware complexity scales more efficiently than state-of-the-art RowHammer mitigation mechanisms. We conduct cycle-level simulations using Remulator and DRAM power to evaluate the performance and DRAM energy consumption. We simulate a realistic system with a DDR4 DRAM module, and we use single-core workloads from 4 benchmarks in our simulations, namely spec benchmarks, disk I/O memory traces from YCSB benchmark suite, memory access traces collected from a network accelerator chip, and synthetic traces that mimic bulk data copy with non-temporal hint. We randomly combine these workloads to create 2 types of 8-core multi-programmed workloads. Workloads that contain 8 benign applications, and workloads that contain 7 benign applications along with 1 thread performing a RowHammer attack. We start with evaluating for single-core benign workloads. We classify single-core workloads into 3 categories based on their row buffer conflicts per kilo instruction, and we evaluate the performance and DRAM energy consumption for BlockHammer and 6 state-of-the-art RowHammer mitigation mechanisms. We observe that no application's row activation count exceeds BlockHammer's blacklisting threshold. Therefore, BlockHammer does not change the performance or DRAM energy consumption for single-core benign applications. We evaluate all these mechanisms on BlockHammer for 8-core multi-program workloads under 2 conditions: when there is no RowHammer attack and when there is a RowHammer attack present. We use 4 metrics in this evaluation to demonstrate the system throughput, job turnaround time, unfairness, and DRAM energy consumption. When there is no attack in the system, BlockHammer introduces very low performance and DRAM energy overheads. And when there is an attack present in the system, BlockHammer significantly increases benign application performance and reduces DRAM energy consumption. We conduct a scalability study with worsening RowHammer vulnerability as well. And again, we consider the cases where there is no RowHammer attack and when there is a RowHammer attack present. In these tests, we scaled the RowHammer threshold from 32K down to 1K. And here are the results for system throughput, job turnaround time, unfairness, and DRAM energy consumption. We observe that BlockHammer's performance and energy overheads remain negligible even when RowHammer threshold is scaled down to 1K. And BlockHammer scalably provides much higher performance and lower energy consumption than state-of-the-art RowHammer mitigation mechanisms when there is a RowHammer attack present. We provide more analyses and implementation details available in the full paper. First, the paper shares a security proof where we mathematically represent all possible access patterns and show that no row can be activated at a high enough rate to induce bit flips when BlockHammer is configured correctly. Second, the paper explains how BlockHammer addresses many-sided attacks by tuning its thresholds. And third, we evaluate all 4 high-level RowHammer mitigation approaches through analyzing 14 mechanisms from 4 aspects: comprehensive protection, compatibility with commodity DRAM chips, scalability with worsening RowHammer vulnerability, and deterministic protection. We show that BlockHammer is the only mechanism that satisfies all of them. In conclusion, this paper tackles RowHammer as a worsening DRAM reliability and security problem, while state-of-the-art RowHammer mitigation mechanisms face limitations supporting current and future commodity DRAM chips due to their limited scalability with worsening RowHammer vulnerability and limited compatibility with commodity DRAM chips. The goal of this work is to efficiently and scalably prevent RowHammer bit flips without knowledge of or modifications to DRAM internals. Our key idea to achieve this goal is to selectively throttle memory accesses that may cause RowHammer bit flips. Our mechanism BlockHammer performs 3 operations. First, it tracks activation rates of all rows using area-efficient Bloom filters. Second, it throttles row activations that could lead to RowHammer bit flips. And third, it identifies and throttles the threads that perform RowHammer attacks. We evaluate BlockHammer's scalability with worsening RowHammer and demonstrate that it is competitive with state-of-the-art RowHammer mitigation mechanisms when there is no attack in the system, and it provides significantly higher performance and lower DRAM energy consumption when a RowHammer attack is present. BlockHammer is compatible with current and future commodity DRAM chips because it does neither require proprietary information of DRAM internals nor modifications to DRAM circuitry. And this concludes my talk. Thank you for your time and attention. For many more details, I invite you to read our HPCA 2021 paper.